Hello, sir.
Hello. How are you, Dr. Ghosh?
I'm doing great, sir. Thank you.
Okay. Did you visit IIT Delhi in the meantime, or you are staying here only?
No, sir. After 2017, I have.
Okay. All right. So fine. So you are free of that chilly winter and all at Delhi. Winters are better now.
Yeah.
Okay. Fine. So all right, Professor Roy is there who
Yes,
will
sir.
introduce you formally. Yeah.
Okay.
Okay. Thank
Thank
you
you.
for joining, Dr. Ghosh. I mean, thank you for accepting our invitation and joining. Thank you
No,
very
sir.
much.
It's my pleasure, and it's been
Yeah.
a really good opportunity for us to present
That's
and
wonderful. That's wonderful.
represent their certification.
Fine. Thank you.
So thank you, sir. So good evening, everyone, and Dr. Ghosh. So before that, I will introduce a bioprofile of Dr. Sarvani Ghosh. She has received BTech degree in Electronics and Communication Engineering from West Bengal University of Technology, Kolkata, and MTech in Communication Engineering from National Institute of Technology, Kurukshetra. She earned her PhD degree in electrical engineering from Indian Institute of Technology, Delhi. She was a national postdoctoral fellow at the Indian Statistical Institute, Kolkata, 2017 to 2020. She received Best Paper Award in Women Engineering in IEEE ANTS 2017. She co-founded the DSZ Innovation Laboratories Private Limited in 2022. Her research interests include physical layer security, cooperative communication networks, performance analysis, reconfigurable metasurfaces, cognitive radio networks, energy harvesting, and performance optimization in 5G and 5G networks. She has large number of publications in IEEE transaction on cognitive communication and network and IEEE transaction on wireless communication. She has been actively reviewing papers in IEEE venues for last 10 years. The list includes Globicom, BTC Fall, BTC Spring, WCNC, and ICC. She has also served as a TPC member in WTC Spring, WTC Fall, and WCNC. So this is the brief profile of Dr. Sarvani Ghosh. Now, Ghosh, the session is yours. You may continue.
Thank you, sir, for the warm introduction. So this is the fourth day of faculty development program. And my topic of discussion today is 5G and 6G for cloud computing, keeping in mind Industry 4.0. So let me first start today's discussion with this diagram, which shows a factory floor which is being automated. And we do not know how this communication or the whole maybe designing will take place, where we have an access point, something called as IRS, and how this robotic arm is going to actually deliver its goal. Then we shall get to know it through possibly through the and throughout the discussion, and maybe towards the end when we reach there, maybe that will serve as a hand holding for the whole motivation. Coming on to the next one, this also shows another factory floor which is going to be refurbished. Here you can see there is a wireless energy transfer. I shall explain it shortly. With data beam, and there is enough or plenty of data to be offloaded from all these industrial devices, and how the communication is going to take place using an access point or base station. There is another machine edge their server there, which will help us for computing, and how the whole communication process will take place is possibly going to be discussed in this session. So first, I start with introduction to 5G and 6G. followed by what is meant by telecom generation, its evolution, what 6G means to different group of people, what basically is the second part of today's agenda, that is cloud computing, and what is 6G, which is going to be finalized by the end of 2030, and what are the enabling technologies for that particular generation, what are the possible challenges, and how research trends it's going to continue over that direction, and what are the possible opportunities for that. So this diagram shows us the evolution of wireless networks. First generation was analog voice call, and AMPS stands for Advanced Mobile Phone System Standard, where the data speed was less than 2.4 kilobits per second. It had analog communication, supporting only single voice communication, and frequency division multiple access was the enabling technology communication platform for that. For the second generation, we had voice coupled with SMS, that stands for short message service, which later was transferred to MMS, which is multimedia messaging service. It was introduced a little later. And for the second generation, the speed was less than 64 kilobits per second. There are certain number of standards here. As you can see, this TDMA, which was time division multiple access, which is a better version of frequency division multiple access. GSM I have already explained, and there is this ADG edge. This is different from what we see in today's edge network. It's an acronym, and it stands for Enhanced Data Rate for GSM Evolution. And this was typically for 2.5G moving towards 3G. Later on, it was GPRS was introduced, which stands for General Packet Radio Service, Internet Access over Cellular Networks. All these generations talk about how different devices was little late, came on a little later, maybe end of 4G towards 5G, 6G. We talk about devices, but previously it was cellular devices, cellular phones, and all about communication over cellular networks, which had a hexagonal structure. Coming on to 3G, it has evolved from voice services, SMS, MMS, to connecting over the internet, and it had standard as Universal Mobile Telecommunication System. It now supported 200 megabits per second, supported by the WiMAX, which was at that time Colloquial was used later as Wi-Fi. It supported data, voice, and video communication, all three. From 3G, we later had 4G. 4G had WiMAX, LTE advanced, and data speed or data rate was supported, which was a little less than 2 Gbps, gigabits per second. Coming on to 5G, 5G had beam division multiple access instead of frequency division or time division, and then code division was part of 3G to cater to a large number of users. It also slowly SDN was being built in 5G to separate out different users, requirement, heterogeneous users, etc. So software-defined networking was introduced. And more or less, sometimes we hear about millimeter wave, and throughout the discussion today also we are going to encounter that term multiple number of times possibly. So I'll explain briefly what is millimeter wave. It is basically a part of the electromagnetic spectrum, which has a very short wavelength of the order of 1 to 10 millimeter and very high frequency, 30 to 300 gigahertz. But there is only one catch here, that it performs very poorly when it meets with an obstacle. It has very poor penetration capability. Coming on to the terahertz domain, which is part of the key feature of 6G, which is of the order of 0.1 to 10 terahertz. Terahertz means 10 to the power 12 hertz and has wavelength of 3 millimeter to 30 micrometer. Moving on, here in this slide, I shall be comparing industrial revolution along with mobile generations. So as you can see, from 1980s to 2000, we had industrial revolution version 3, which included electronics and computers. By using computers here, I mean computers were used for record keeping, for deriving designs for manufacturing industry, etc. While for mobile generations, it changed every decade starting from 1980. 1G had analog, 2G had digital SMS, etc. For 2000 to 2010, we had 3G, which boasts of mobile internet starting age. And from 2010 to 2020, we saw the advent of 4G with long-term evolution broadband. And from 20 to 2025, possibly we are seeing 5G, which key features enabling technologies that boasts of connecting millions of internet devices, Internet of Things, and supporting low latency applications. And towards the end of 2030, we shall possibly see 6G with AI, artificial intelligence, which understands and collaborates and computes using AI native networks. So now there has to be a hand-holding between 5G to 6G and Industrial Revolution from 4, which is ongoing, to Industrial Revolution 5, which talks about complete human-machine interaction, fully automated community. So the major driving force and transformation from fifth generation, or the industrial automation that we are talking about, Industrial Revolution 4, right? Industry 4.0, that talks about automation and control into cyber physical manufacturing systems. Maybe yesterday or day before yesterday, we had a session on cyber physical systems, which was delivered by Professor Dr. Ashish Kumar, possibly. And this leads to a point that with introduction of private 5G wireless networks into industrial environments, we can see a proper leading technology taking shape. So these are the features of 1G, 2G, and 3G, which I have briefly explained in the first few slides. From 2G to 3G, we can see the whole information was packetized, formed into different smaller packets to transfer data, video, web browsing, etc. So these were from 1G, 2G, 2.5G, 3G, and up to 4G, which had only 100 megabits per second to 1 gigabits per second. Now, which slowly led towards the streaming platform, online gaming, and voice over long-term evolution, voice over LTE communication. 5G, which is the current technology, which is still a little bit developing phase. It is ultra fast. It has data rate or speed or capacity, channel capacity of the order of gigabits per second. It has little low latency, 1 to 10 millisecond, and it supports millions of devices which can be connected over the internet. That is also why they're called Internet of Things. There is also artificial intelligence and AR, or augmented reality, virtual reality, which will take shape little better in the next generation for 6G. There's also Smart City 2.0 in the talks, and autonomous vehicles. So talking about in 6G, what is to be expected? We expect that there will be better integration of automatic and high precision manufacturing processes, which will integrate machines and humans into their control loops, and possibly obtain little low latency as was promised in the 5G networks. with high reliability. So what 6G means to different groups of people? If I am a domestic consumer, 6G would possibly mean an ultra-fast network with whenever I request a near instant delivery of requested information, and also immersive connectivity that is completely seamless, uh, without any disruption, interruption, and making everyday life little easier. Let's call it digital experience, quality of experience, that we call it in terms of communication jargon. That experience has to be seamless, intelligent, and has to be integrated with our current reality. For an industrial consumer, which is typically maybe in manufacturing, it could be a healthcare unit, it has to be hyper reliable, meaning that the loss rate has to be of the order of, say, 0.001%. So means in 1,000, there can be only one error. Very low latency of the order of 1 millisecond. And if it is driven by artificial intelligence, it has to have that seamless connectivity, which enables autonomous operations, real time, which is real time, which involves remote robotics to operate a patient, and mission critical decision making, which means that your uh, operation has to be completed within a given time. You do not have another shot at the problem. Okay, coming on to the system integration engineer, the whole system perspective includes building a system which boasts of interconnectedness, which is software defined, which uh, separates out control plane from the user plane and divides the user plane into possible into all the users, that user facilities or services that are being requested instantaneously. There has to be integration among the system components, which are, say, networks. Different networks have different service qualities. All those have to be taken care of. Each network consists of different number of devices with sensors. I'm talking about physical devices here, different sensors. And coming onto the network layer, also the cloud or edge, which can be manipulated or used to obtain a low latency using artificial intelligence. Now, all these components, be it in the physical layer or the data link layer, up to the network layer, all these components have to be integrated with latency and interoperability, keeping in mind also the performance metric for different layer varies. As far as a computer science engineer is concerned, a 6G will mean a newer architecture, which is really different from 5G, which talked about ultra reliable, low latency communication. Now it is about terahertz communication, which integrates artificial intelligence, millions of numbers of devices, which are automated, and distributed computing models, and talk about a little bit about age native software paradigms, which supports billions and billions of real-time data processing, and all these applications have to be connected to. Okay, for an AI engineer, what it means is that we have access to always on, that is what is meant by ubiquitous, always on, ever pervasive, and real-time data streams. Next one is edge intelligence, which enables powerful, responsive, and AI models that are context aware. Now, from the perspective of communication engineer and researcher, the 6G talks of how to push the envelope for in terms of wireless technology with newer spectrum. Why newer spectrum? Because we now have different user categories, different number of really high number of users. So each user will consume certain bandwidth, and therefore there is a bandwidth or the spectrum crunch. So we need a huge range of frequencies for that, and that's where terahertz comes in. Now, it also requires advanced amount of advanced waveforms, which is very different from previous architectures, say FDMA, TDMA, etc. It also calls for intelligent surface. So this is a relatively newer technology, which was introduced in 5G communication during that generation, maybe 3-4 years earlier. And it has actually multiple, it is actually linear array, which consists of passive elements, which draws very negligible amount of power, but still points a very sharp beam as if towards the intended user, consuming very negligible power. So that's what is intelligent surface for a precursor. And using for a communication engineer, I'm also interested to understand or fathom what AI can do in terms of network optimization, optimize a particular objective, keeping in mind the constraints, be it computation constraint, be it interference constraint from other devices, from other or nearby cells. How does that work out? So now coming on to cloud computing, how cloud computing has been integrated into fifth generation of telecom networks is that now previously it was MEC was machine edge computation. Now we call it multi-access edge computing. This is basically low latency computation performed at the network edge. It supports real-time loads, and it actually offloads its computation things to the cloud. So as you can see, there are different latency requirements for different applications. Say if it is automotive driving or IoT or gaming, we need latency which is less than 5 millisecond. For augmented reality, virtual reality, medical applications, we need little less than 10 millisecond. And for video analytics, we need 30 milliseconds. So if you can see typical radio access networks, which are these base station or access points, these are radio towers. These are connected to fog computers. These are central offices. These are fogs. And these are wired connections from on-site services, say manufacturing or plant. Will be connected to a fog, and regional central offices and connect to a core, which is further connected to a cloud. So the thing is, this is the thing. So if it is of low computational complexity, then these fogs are sufficient. If not, then we need to go to the cloud, perform that computation, and get that result back to these nodes, these radio access points and devices, so that they can take a particular action, perform certain actions, take a decision or control, etc. Okay, sometimes or we are commonly now incurring this term latency. Latency means the time difference or the lag in between at a time when a particular job or a request was received to the time between when it was actually performed and receiving that acknowledgement. So that is basically latency. For 5G networks, which talk the most of ultra low latency, it has to be of the order of, it was promised in the standards actually, that it was supposed to be 8 to 12 millisecond. Ignoring retransmissions, there is congestion in the network, there can be delays, there can be handover errors, which is basically considering an ideal infrastructure. So that consists of low delay core millimeter wave, which I explained a little earlier, mid band, and little low load. But in real world, latency actually depends on a number of factors, which includes network architecture. It could be standalone, with also a non-standalone one, consisting of backhauls, which are wired fiber links. cell tower or load, how much loaded or how much overpowered your base station or the cell tower is, how many number of devices are connected, what sort of applications they are requesting, what is the geography or of the area, whether there are obstacles in between the base station to the requesting user, and also if there is certain routing, what should be the logical path or route in between different users, can there be multiple number of relays in between, and how much is the server distance. Hence the actual perceived latency was much more than what was promised. So this is where edge, fog, or cloud continue comes into picture, because latency was, the derived latency was quite more than what was promised. So in real-time data, edge processed that information, fog was the intermediate layer, and cloud is the large-scale computer which are there to compute, perform computations which are quite complex, which takes really good amount of time. So clouds are the data centers, which could be in number of thousands, whereas your devices or the mobile devices, or it could be your laptop, your desktop, etc. It could be billions number of such devices which are connected to fog nodes, and these fog nodes are typically in a number of millions. And these fog nodes requests are sent or pushed to the cloud data centers, which perform computation and gets back to you to do the intermediate fog layers, and which are to be in the next step, which are sent to the edge devices about decisions, about the processing, how data are processed. All this information are then sent to the next layer, which is the actual requesting device. So now this lays the foundation of an enabling a technology, which is the cloud computing, which is part of 6G, which can be part of 6G, to aid the communication process. So for 6G, which has millions of devices, you are just generating a huge amount of data. So, but still that data needs to be acquiesced, means you need to acquire that data. For that, you need a physical device, an IoT sensor, etc., that has to be managed or engineered regarding about its power level, etc., how the information can be detected there. What is the reliability of the data decoded? How timely your data has been collected, because after a certain amount of time, the sensor information will definitely change, and whether the information has been delivered to the base station or the data center in a timely manner or not. So that's where the latency, the need for cloud computing, the need to integrate with 6G comes in. So as I explained, that's for 6G, the core technology is a terahertz communication, which has this 0.1 to 10 terahertz frequency, a huge frequency bandwidth. And of course, the wavelength is inversely proportional to the bandwidth. So wavelength turns out to be 3 millimeter to 30 micrometers. And this is a full to play communication, means that you can listen and talk at the same time without interfering these two operations, without actually hearing yourself. There has to be sufficient noise cancellation and successive interference cancellation taking in, which is actually running in the background, which lays the foundation for full to-play communication. So the listening takes place in a particular frequency bandwidth, while the talking takes place in a other bandwidth, which do not interfere with each other. That's how the design perspective goes. Okay, the network has to be optimized, means that your design goal can be different. It can be since I'm a communication engineer, I always talk about this data rate or the signal rate that is received, which is typically measured in dB, decibel scale, or it can, which is basically the measure of signal quality. And now, if you talk about the quality of experience, then maybe I shall talk about throughput or minimizing latency. All these terms are associated with the or network optimization. These are my design objectives. Now, for different networks, say if I'm talking about a cognitive radio network, say the same spectrum or bandwidth is being shared among multiple number of devices. So there can be certain licensed users which are to be part of the network, and some unlicensed user which request the services whenever the network load is not that much. So the whole bandwidth is to be shared among them. So the unlicensed users come and pay the licensed users, not actually pay the licensed user, pay the network service operator some amount in terms of the bandwidth. Actually, bandwidth is being leased to those unlicensed users. So their power level should not be interfering with the licensed user's one. So all these constraints have to be taken care of while we design a cognitive radio network in different modes. Next comes holographic telepresence, and cobots are collaborating robotics for the next 6G, which are to be part of the core technology, smart grid, second generation 2.0, and autonomous vehicles. So we have more or less heard about UAVs or AAVs and all these related terms that which had autonomous aerial vehicles, you know. So that's also part of 6G, which has which are usually used in mission critical applications. And of course, there is another thing which has spatial communication, which involves space to air, to ground, to sea networks, which involve satellites, your ground stations. And there is something in between which is not as powerful as the satellite, little less, which is the high altitude platform or HAPS, which help just as fogs help cloud. This is just another part of the 6G communication. All these are say speculated to follow that minimum latency and maintaining a certain throughput. So now this is a diagram of a smart factory. As you can see, there is an automated guided vehicle which is connecting among different devices. And this is inventory management. All these are digitized. All these things are connected digitally through the internet. Everything has a particular antenna, maybe single or multiple. There are sensors, and there is an assembly line. All these things are connected. Okay. Now, what happens behind the sensing and communication unit? I shall briefly talk about that a little bit. For the network layer, you can see there is a USB or sensor node, which has energy efficient routing. So energy efficiency is another term, another objective, which is being used nowadays. The enhanced data rate doesn't always mean that the communication is energy efficient, because all these devices, no matter how small they are going to consume certain amount of power in energy in for a certain span, because energy is equals to the power consumed multiplied by time that they are on. So energy, as well as the base station, as well as the enablers, let's call it the IRS, or it could be active relays, which are part of the whole system, whole communication ecosystem. So to maintain higher throughput and also an energy efficient communication, we need to think about from the perspective of both throughput or data rate as well as minimizing energy. So it's a conflicting thing, because you wish to increase or get better throughput. Obviously for that you need more amount of power, but more amount of power means that you're drawing more energy from the network, which is not green, not sustainable. That's why you need to minimize your total energy consumption as well. And if you want to look at it at one shot, then energy efficiency is the go-to objective for that. So if I am to look at a node level or a bit level communication, we can see there is a battery which has to be converted, battery level has to be converted. This is the power unit of the sensor or the sensing unit. If we talk about unit level, it has to be converted into from DC to DC power. And this, for sensing units, the sensors have to be different sensors for different applications. For smart sensing, all the sensors sensing information has to be digitized from analog. It has to be converted into digital. There has to be a processing unit which converts the data and stores this into particular memory, which can be further analyzed later. And this is the communication unit, because all these sensors, as you can see, have a single or multiple antennas. And this is basically a transceiver, because earlier I talked about full duplex communication, which means both transmitting as well as receiving. So to optimize your radio performance, you need to typically select or think about, keep in mind duty cycling. It's because all these devices are always on. So you need to uh, properly tune their duty cycle, so that even if they're always on, there has to be certain wake up receiver. It's not that all the devices are on all the time. So if you want to efficiently manage energies, then you have to design their duty cycles efficiently. So in that case, because all these devices are battery limited, they have limited power in terms of battery, and all these batteries, it can be such that these devices are placed in a very difficult terrain, which are not always reachable, and these batteries cannot be replaced all the time. So you need to design their wake up and sleep cycle accordingly. So that's where the ultra low power wake up receiver design and power designing and optimization comes into picture. So this is basically a large scale design in that perspective. I shall briefly talk about this uh, reconfigurable intelligent surface, because this is such an integral part of 5G. It and because of its ability and how it has been designed. So RIS or IRS or LIS, as it is commonly known as, these are the three acronyms for it: Intelligent Reflecting Surface for IRS and Large Intelligent Surface for LIS. It has the ability to improve wireless network performance, maybe in terms of let's call it, be it throughput or data delivery in particular time, or be it another objectives such as energy efficiency or total power consumption. It can create a controllable radio environment which can be easily maneuvered, because RIS consists of multiple number of, say, n cross n. If you have n number of rows and n number of columns, typically then you have n cross n number of elements, which means that your reliability, even if one path from this transmitter to the receiver is absent, say this is the direct path, which is known denoted by the HD. This is direct path. If direct path goes through certain obstacles, then you do not have any communication from the transmitter to the receiver. It's completely blocked. So then risk comes into picture, which can be typically installed on the facade of a building or inside, even in an indoor environment, on the walls. Yeah, risk can be, or a patch, or the controller can be installed, which boasts about n cross n number of antennas, basically, which are passive elements because this consists of uh, PN junction diodes with certain intrinsic element in between. PIN diodes are varactor diodes, which draw very negligible amount of power. So basically it beam forms from the transmitter to the receiver, forming a particular beam into a particular direction, and it's governed by Snell's law. So these are programmable surfaces, which whatever being incident on this surface are re-engineered to form a beam into a particular or desired direction, which obviously boasts of improved amount of coverage, signal coverage, and improved beamforming without needing multiple number of antennas at the reflecting surface because it already has multiple number of reflecting elements. Now this can be passive risk as well as an active risk. Active risk draws certain amount of power to uh, do some other uh, functionalities added on top of being only reflecting. It can reflect and transmit as well, but I shall not go into that detail. So real world examples across industry involving risks as these typical examples. Okay, so from a base station or an access point which has multiple number of information for multiple receivers, there can be base station to base station interaction, as you can see in figure A, involving distributed IRS. This is a direct link, and if direct link goes through an obstacle, there is another reliable link such that you do not miss out on information. You do not have to retransmit your signal in that way. So, and scenario B has a base station communicating to UAVs. There can be direct path or LOS path that we typically call in the jargons of communication engineering. So this is another way, frontal link as well. We call it frontal link. So from base station to IRS, we have one or the first hub, and from IRS, which reflects the signal towards the UAV. So even if there is an obstacle in between, you get to have better signal quality. So there is this C scenario, which has multiple number of distributed beamforming via IRS, multiple number of IRS on these facades, although there can be multiple number of reflectors in between. As you can see in this C diagram, these two persons are located in two different rooms, but if there is an iris in between, then even if there is a partition in between them in the same room, message can get delivered. Okay, this is a typical roadside unit in 5G environment. UAV gets that virtual line of sight communication using IRS, both UAV and IRS as the enabling technology here. Okay, this is a typical security constraint scenario where we have multiple number of users, but one of them, it could be a passive eavesdropper. So you do not get to know which one is inside your system is listening to the communication and tapping it, maybe not changing the whole signal, but actually listening to the whole communication and tapping it. So if you have an IRS can project the signal beam towards the intended user and block the eavesdropper by sending an interference signal towards the eavesdropper. Okay, moving on to the first figure that we saw. So now I think a little bit has been clear with enabling technology, which is which was explained in earlier slides, which is the intelligent reflecting surface. So even if you have a factory floor which you are refurbishing, this robotic arm knows what to do, and when all these things are being moved around. So even if there is no line of sight communication between the robotic arm and the access point.
Dr. Ghosh, Dr.
Yes,
Ghosh,
yes, sir.
I'm not too sure. For quite some time, I don't see that slides are moving. I don't know whether you are changing there, but it seems that slides are not moving for quite some time. I mean, would you kindly look at?
Okay, sir, I shall stop sharing and share my screen again. So can you see now?
Okay. Acha, then okay, fine. That means, all right, that was a slide. My impression was that you were talking from some other slide. Okay, fine. Carry on, please.
Yeah, okay. No, actually, I am repeating the previous slide which you saw.
Okay. All right, all right, all right. Please carry on. Please carry on.
Okay, all good then.
My bad. My bad.
Okay, no, sir, no problem.
Okay.
So I have again shown you the previous picture which I showed you in the beginning of the slide. So this is an automatic plant reconfiguration being taking place when due to a different production demand. So things have to be moved around, but this robotic arm, there can be an obstacle because all these things are being moving around, and this is electromagnetic wave that we are talking about, which goes through multiple numbers of scattering, diffraction, reflections, etc. So the quality of signal or signal strength that we receive at the robotic arm may not be sufficient for it to function in a particular manner. However, if you have an iris installed on the wall of that particular room, then you have a virtual line of sight, which is the non-line of sight beam here from the access point leading to the iris, and it has multiple number of reflecting elements. So it forms a beam towards somewhere reaches the robotic arm through multiple reflections, etc. Iris assists in that coverage location, covering that particular moving user so that it performs up to the mark. So this is the iris assisted beam, how it performs, even all this, even though these things are being moved around. And I have taken this diagram from IEEE Communication Magazine, which was published in 2022 toward Industry 5.0 Intelligent Reflecting Surface in Smart Manufacturing. And going to the next one, this has multiple design aspects. Although we see there are multiple number of robotic arms here, and iris boasts of communicating from the access point or base station, forming a data beam as well as an energy beam, because all these devices have a certain battery in between them, embedded in them actually. So this signal actually can be engineered into forming two different objectives. One is to transfer power and transfer information. So we call it as SWIPE, which stands for simultaneous wireless and information power transfer. But using the same signal, you can power the device, you can power certain devices while transferring information to some other devices. And it can be used, this can be solved using certain scheduling techniques. Of course, there is data to be offloaded from the device to the access point. There is obviously energy beam and data beam that I already talked about. The data from the device has to be sent to the access point, possibly using an iris because there are blockages in between, which hinders the line of sight communication. So the distinguishing signal among different devices are to be taken into account, because each device has its different frequency. And where is that device actually located? So that forms the premise of localization sensing. And there is an MEC server, which is co-located with the access point, which performs the processing or high computation things, which is again RS assisted coverage. So all these 3-4 things uh, can be a design objective for the futuristic 6.0, which clubs or takes into account machine edge computation and 5G, simultaneous wireless and information power transfer to 6G. It could be URLLC, it could be through terahertz communication. So, yes, the major driving force and the transformation from industrial automation and control into the cyber physical manufacturing systems has been 5G. And that's possibly going to lead to maybe of having a private 5G wireless networks, which integrates, which can be easily integrated into industrial environments. So 5G brings into picture the cloud native networking, and 6G will be more conversant with AI, automation, terahertz driven technologies, which is powered by edge computing, which is really essential for having that low latency processing. Yes, sir.
I think someone has unmuted. So, Professor Dilma, could be there?
আচ্ছা ঠিক আছে বেরিয়ে আসেন আপনি যান
So, okay, thank you for being patient and listening to the whole discussion. And if you have any questions, I'm ready to listen to the query and answer.
So, first I would wait for the participants to ask question. Then I have few queries. But first, first let the participants ask questions. The participants by now are have learned a lot, I believe, and therefore more or less conversant with some terminologies. But maybe one thing I would like to possibly request, I don't know whether the request is valid or not, or maybe people already know, but I believe that people have joined from various different disciplines. So some explanation possibly would help to say, for example, I don't remember all the points where the clarifications are necessary, but for say example, that where people classify between fog and cloud, so some people might need to understand a bit more what is the difference between fog and cloud. Does it make sense, Dr. Ghosh?
Yes,
Yeah.
yes, sir.
So
Yes, sir.
since it is your area, you are going very fluently with it, very comfortably. But maybe some people are struggling there. Maybe I do not know. It may be a hypothetical question, but whatever, it appeared to me to be a valid one. So if you care to respond to this, please.
Yes, sir. So I am basically from a communication background, and this fogs, clouds are typically used as computer science jargons, but I am slowly
Yeah.
learning them, as I know that fog is used as a handshaking towards a cloud, which is a more robust platform as compared to fogs. And suppose if you have a very not that much computation expensive as well as extensive, I would call it, because each computation requires certain amount of power. Uh, so fogs are those which are located near to the users where they are. So and they are also very limited in terms of their numbers. And if you have a very small requests and computations which are usually done over the period over on an average, so then your edge servers are conversant with those requests and with those computations. So you can get that back very easily and in a little less time. However, for cloud computations, regarding the huge volume or huge amount of data that is being generated from sensors, because you need to interpret and understand what should be the next step or next action that you wish to do. And in terms of that, how to store that huge amount of data, you need a cloud. And also, if you have those many numbers of devices, those many number of iris, and also I forgot to mention about certain one thing, which is again a communication jargon, which we call it as channel state information. I do not know from the base station perspective where my requesting users are. So I first need to understand where my user is, because I certainly need to send some control signals where they are, yes, no, from those device, yes, no, handshaking, uh, transmissions from binary transmissions from those devices as well. But I do not know which device is talking to me. So firstly, I need to localize that device where it is actually, if it is a static scenario that we are talking about. If it is not a static one that users are coming and going, then it becomes even more difficult. So all these computations, all this knowledge has to be stored somewhere. All these iris elements that I talked about, sir, right, which has maybe of the order of 2 to the power n, say 128 or 264 number of elements, and multiplied by all this devices. So it's a huge amount of data to actually process. For that we need a cloud to store that information, where actually the information was requested from, whether it's temperature data or a motion data, or which sort of data it is for labeling and typing and this request. And because it's a heterogeneous user kind of situation, I hope I does that answer your
Yeah,
question,
perfect,
sir?
perfect, absolutely perfect, Dr. Ghosh. I mean, this brings clarity because see, I understand not all from computer science background exactly, but it is interesting that uh, people from various disciplines to come together to implement Industry 4.0, because it is not exclusively to one domain or to one discipline. So it is always good to see that, an interdisciplinary approach, and also the understanding of the terminologies or jargons, if you may say, of sister disciplines or correlated or associated disciplines.
Mm-hmm.
uh, just one thing that it is intriguing, although you have mentioned, but I do not know whether any um, assessment has been made in terms of, say, for example, the autonomous car that you have referred to, or say, for example, the mm, AI
Yes.
effectiveness. See
Yes.
how much in terms of quantitative terms, really, in terms of either speed or whatever. would be the improvement from mm, level 5 to level 6?
Improvement in terms of yeah,
Response or speed uh, or precision or in whatever parameters.
yes,
You can decide your parameters. I perhaps am not mentioning all the parameters,
yes,
but how much improvement is expected or are being predicted, that is important. Because see why I am raising this question, because now also people are using AI. Now also people are doing autonomous cars, and they are working. They are working. In fact, in fact, we have set up an autonomous car system in our laboratory here at
yes.
Seacom Skills University in our emerging technology lab very recently.
Okay,
We are using um, uh, this Jetson Nano as the processor. Okay, which is
okay,
an improvement from Raspberry Pi.
okay.
Yeah. So that is giving us a major improvement already. So how much further improvement is expected when we move from the next to next level?
Uh, sir,
My,
yeah,
possibly I have been able to put forward my queries. It is not a question; it's a query,
yes,
because we are already doing it and it is working. But now,
okay.
how much in what parameters the improvements are expected, or you want them to be?
Yeah, if I talk about Industry 4.0 to 5.0 in terms of data rate, for 4.0, it was envisioned as 10 gigabits per second. It can be in the scale of 10, multiples of 10, be 100 gigabits per second for 5.0. And in terms of latency, uh, it could be, it was previously promised as 100 millisecond, something like that, to 250 microsecond, some in certain standards. For 5.0, it could be less than 100 microsecond, of the order of that. If we talk about reliability in terms of packet loss rate ratio, for 4.0, it was 10 to the power minus 5 or 10 to the power minus 8, which means one error in one 10 to the power 5 bits or one packets. And up to for 5.0, it is it's still in the nascent phase. It
Mhm.
can be of the order of 10 to the power minus 10 or something for in terms of packet error rate while detection. In
All
terms
right.
of connectivity density, it was one device in a square meter area to 10 devices you cater to in a square meter area. For
How much?
energy
How many
efficient,
devices? How many?
10 devices in a square meter area for 5.0.
Okay. Okay.
And
Okay.
for energy efficient communication, it was 1x for 4.0, then
Mm,
10 times of that, of what was promised in 4.0.
I see. I see. So overall improvement, if I have done a very rough mental calculation, is nearly 5 times.
Yes, sir. Uh,
So
yeah.
so I mean, would it help? Therefore, I am sure it would also help since the speed is that high. I believe it will also help in reducing the energy consumption. Does it?
Yes, sir, it does. Because energy for in terms of devices and in terms of the passive things, in terms of yeah, if it is being done by those fog instead of cloud, then yeah, truly. In terms of devices which are whose sleep cycles are efficiently managed, then yes, the more number of passive devices you have, yes, less consuming energy. So which also means that you have a base station which will not need that much of power which used to need earlier. Now previously it was for third and fourth generation, it was quite high. Now we talk in dBs. Now we talk in dBms. So base station loads has also been reduced. Now also another thing I would want to mention here, since communication engineering has been the enabling thing that we talk about here, is that one cell has been divided into different smaller cells. So the load that was on previous base stations is now being divided among different number of base stations. So one cell, previously we used to talk about cell reuse. Now we have microcell, picocell, nanocell, that sort of concepts. For a typical service management, we divide our cell where it is being actually originated from. The requests are being suppose originated from a cell A. So we divide A into different number of smaller cells. So smaller cells have smaller other base stations. So not the main or the singular base station is not being overloaded that much. So that way you can say that it is also energy efficient. And not all services are being requested at the same time and all the time. So scheduling, task allocation, yes, task allocation is another thing that goes hand in hand with cloud server adjustment and collaborations. So
And
in
one
that way.
thing that in connection to this that I was about to come, because why the energy aspect is important, I feel, is that quite a few things are related to this. See, there are certain equipment for their safety measure. When the energy flow is high, it is
Yes,
found that it heats up, its temperature
yes,
goes up, and
yes.
it shuts down. The system is designed to shut down,
Yeah,
to prevent. Now, if the energy consumption goes down, then that problem also will be largely reduced.
sure. Absolutely.
And in many electronic devices, possibly you know very well, because you being a communication electronics engineer, that this thermoelectric devices are used in order to keep that balance in terms of heat and temperature.
Sure.
That's a big challenge now, huge challenge in, see, in this particular aspect. I think it is a very common ground for the research of electronics and mechanical engineering, because I find mechanical engineering are doing fluid dynamic study to look at the heat aspect of this electronic package controlling, temperature controlling. So, what is your take on this? I mean, how much miniaturization would be possible because of this?
Sir, instead of miniaturization, I will say task offloading and efficiently handling this time allocation among devices and efficiently handling the wake up cycle. So, because duty cycle is nothing but time it is on divided by the time it is on plus time it is off. So, if you are able to draw very little amount of power while you're sleeping, because the device is always on, so of the order of microwatt, if usually it takes of the order of milliwatt amount of power to perform certain tasks, to transmit or to receive or to perform certain allocations and this and that. But if it draws microwatt amount of power, all these IoT devices, then it is, I think, manageable. Of course, miniaturization is there, uh, but this time allocation,
But
this sort of
I mean,
scheduling should be taken into account.
my point was, I mean, even if the miniaturization is possible to the tune of say 10-15%, which may
Hmm.
not be very significant, but even if 10% miniaturization is possible, then actually the other the conditions, design conditions will be satisfied to a substantial extent, that is reduction in weight of gadgets,
Yes.
particularly when it is actually used in conditions where weight aspect is very important. I just wanted to explore that space. So I wanted to have your view on this. That's all. I mean, because see, we often hear, you see, because see, there are applications which are uh, over the ground, AGVs, or it is under
Yes.
the under. So there, I recently was talking with a person who actually is facing this problem at it was at NIT Agartala.
Okay.
It's a very interesting issue that a person, I mean, it's a fantastic one. The thing is that because of the miniaturization issue or that volume issue or weight issue, see, a component that is manageable up to a point in manufacturing, because the sealing becomes a challenge,
Hmm.
underwater
Yes.
in particular. You
Yes.
understand?
Yes.
Sealing is a challenge, and sealing, that means there's no water goes into the system. If moisture goes into the system, the entire electronic circuit will be
Sure.
dysfunctional.
Absolutely.
So see why I am raising this, because one thing in technology is connected to other, and his challenge was, I of course had suggested something to him, but I do not know what he has done so far on this, or he has not given any feedback. But the thing is, say that he has tried a lot many ways, because what he was doing is that if suppose if I seal completely, then I will not be able to repair. Are you getting my point, Dr. Ghosh? That
Yes.
if underwater goes in, then you have to completely cut it off, and that means it is complete waste, and packaging will go, and you never know, in that process the circuitry might be destroyed. But then if I can make such an enclosure that it can be opened also, then the challenge is that how to seal it.
Hmm.
I believe that is also a very important issue in these electronic devices, as we will be extending this industry 4.0 in just not on the factory floor, but also on, say for example, I'm giving one example, that what is that cultivation is called, that I'm forgetting the name, which is done under the water. I mean, I'm forgetting because I'm not from the agriculture side, but um, mm, uh, that's something which grows only under the water, which is also a manufacturing ingredient, a food manufacturing ingredient. Imagine the
Yes, sir.
condition is that while we are using it, is a very interesting case, that when we are producing a good in factory, some of its ingredient resources are coming from underwater. I mean, you understand the situation.
Yes.
And so to check whether that has grown properly or not, so it is actually inspection or quality control based on industry 4.0, and that is to be done underground.
Hmm.
So it is a fantastic problem. I mean, I mean, these kind of problems
You
possibly
need a
will.
sensor, but somehow it should not go haywire because it's underwater. So even if there is a drop of water, then it will stop functioning. That's
It
what you
stop
meant.
function. It will
Yeah.
stop function. It will stop functioning, and and possibly if stop functioning, or it will give erroneous information.
Yes. Yes. True.
It, and
Yes.
and most importantly, if it gives erroneous information, and based on the automatic system runs,
Hmm.
then it would be wastage in huge amount, crores of
Yes.
rupees,
Because you
or
cannot
crores of,
go and check each time, right? If it is to be automated, then it is.
exactly. So I'm forgetting the name of that this thing that we eat.
Sir, are
I
you
mean,
talking about makhana? I do not know.
correct. Yes, lady. Thank you very much. This is makhana. Yes, you are right. You are right. Absolutely right. How do you know it is makhana? You have come across this problem.
Sir, because you mentioned that it grows underwater, it grows
Yeah,
little
yeah.
lower, and it's a common cultivating crop. Not too common. It
Okay,
is
great. I was
Things
forgetting the
in
name. I
Bihar,
was forgetting. Yeah,
Jharkhand.
yeah. I was forgetting the name. Thank you very much for reminding me. I was searching in my mind as to what is it, and that is the problem.
Yes.
So one leads to other. Fine. I mean, okay. I mean, I would leave it to the participants now uh, because they might have questions. Hey, but or
It's a
some
good
questions maybe in
question.
the chat box.
I shall search. I shall ponder over it, and I will get back to you on this, sir.
Please do. This is very helpful because then what we can do is I can pass this information, and already I'm telling you that person wanted to collaborate with us with Seacom Skills University because it is interesting that NIT partner doesn't have a water body, and we have water body here. So
Yes.
they said if such project is received from the government, they will collaborate with us and do it in our water body here.
Okay.
So that's how I come to know various problems, and that is to be integrated ultimately with Industry 4.2 and manufacturing. See,
Yes.
Makhana manufacturing factory would be requiring these kind of devices and arrangements.
Yes. And it is actually because of this sort of supply chain and this sort of management things that come into picture, it is very, very expensive. Although for this alternating food crops, say ragi and millet and makhana, have been uh, really talked about from the government.
Yeah.
Yeah, but maybe because of the chain and all other things, it is really expensive. Makhana
Correct.
is really expensive. So I think possibly and so some sort of insulation should help in, but I'm just thinking aloud. That would be a
Yeah,
possible solution.
or Dr. Ghosh, if you ever come across this problem encountered by someone and they could get some solution, please do let me know. Then
Sure.
possibly we can interact with them.
Yeah, I
That would be.
haven't worked on underwater communication earlier. I didn't get a chance to. But if
Mhm.
I at all get across certain articles,
Yeah, I can
I will
understand.
let you know, sir. Yes.
Uh-huh. But I am putting in your head because see, since you are in the space, you never know. Sometime this thing can come up.
Yes.
I
Yes, sir.
suggested to him something definitely because I went to their lab. I sat with them, uh, and I understood the problem and suggested certain solutions. But
Okay.
well, I don't know. Thereafter, there is no follow up. So
Yes.
that is how it is, where it is.
Okay, sir.
Um, but are there questions in the chat box? But this discussion is very interesting, you see, because see, normally we take very conventional manufacturing, but rather unconventional manufacturing also uses Industry 4.2. That is very interesting. That's why I raised this question.
Yes, sir. Thank you for interacting, and
No,
thank
no,
you for
yeah. So,
getting
but
this.
is there are the questions there in the chat box?
Uh,
Participants are expected to write in the chat box. I don't know whether they have written.
no,
Uh,
I find
Sir,
any.
chat box, is it available, Dr. Ghosh?
Yes, sir. I can see the participants list, etc.
Kundu, Professor Kundu, perhaps you can tell her where the chat box is. I was hearing from him, it is on the right top corner or bottom corner or something.
Yes, sir. I saw that, but I cannot find any questions here.
Okay, but people can ask questions also directly.
Dr. Kundu is there? Deep Kumar Kundu?
Yes, sir. Yes,
Oh,
sir.
so whether chat box, any question is there, you can just
No, sir. There
check.
is no question.
Okay. Ask if anyone has any question, or then we will proceed. Yeah. One can ask the question, Bharwali also.
I
Anything.
have one question, Dr. Ghosh.
Yes, yes,
Regarding
sir.
you are the founder of DSG Foundation,
Yes, sir.
and what is this one exactly what you are doing? Because yesterday we had a good discussion with Dr. Anirban Kundu. He is co-founder of this one.
Yes, sir.
So what is the exactly the business, or what you are exactly the foundation one, how you are doing, what is the works actually?
Okay, so actually we're in the growth phase currently. We are still exploring things and projects, but right now, as you can say, that we are publishing some of this project, some of these ideas into research papers.
Ma'am, I do have a small
I
question.
believe. I
Yes,
believe.
yes,
Yeah. Please go ahead.
Yes, ma'am.
No, no, go
That
ahead.
is, I have heard in some articles that I don't know is this scientific or not, that 5G harms nature or birds in such a way. Is it true, ma'am?
yes, it's true. It has been always there since cell towers have come into existence, and it's absolutely true because it's this highly directional beams that we always talk about, the frequency range and bandwidth, and sometimes it comes with a cautionary feature that do not uh, allow the cellular operators or to install a tower in your vicinity, because then everything goes a little bit of everything has its all these things had comes with certain disadvantages. It harms your well-being, it harms your uh, maybe sleep cycle, etc. It does. And it's true with any electronic devices. Remember your smartphone that you use. The cell towers is truly because it's this gigahertz or terahertz amount of frequency, right? It's highly penetrating. It does. You're correct.
So, ma'am, if we use 6G, that is more powerful that you have said earlier.
Yes.
So it means it will harm us a more in our nature.
Uh, See, not only frequency, the cell tower are also coupled with this power or the transmitter, right? This is a cell tower means it's a base transceiver system. So no, it's not only transmitting, it's also receiving. Transmission power has been drastically reduced by the TSDSI or Telecom Operators Association that we call it, signal, etc. They deal with all this standardization, the telecom standards, and what sort of power the cell towers have to be transmitting in. That has been drastically reduced over the years. And yeah, because I probably I have mentioned this, that previously it was of the order of decibels, now it's of the order of dBm. So if it was, say for example, 1000 milliwatt, then it's 1 milliwatt in that order. And you have multiple number of base stations with possibly not distributing the load and not harming that much.
Okay, madam. Thank you very much.
Okay.
If any question is not there, so can we end the session, Professor then sir is there.
No, you go ahead as you want, Professor Roy, because
Yes, sir.
already enough questions and discussion has happened, and I believe that has added more clarity. And thank you, Dr. Ghosh, for accepting our invitation and sparing your very valuable evening. We have spoiled your evening, maybe, but we have enjoyed this evening.
No, sir. There has been a meaningful discussion, and I
Yeah.
also got to learn a lot while
So
preparing.
do we. So did we. So did we. It's a mutual learning. I mean, we are all learning here. I mean,
Yes.
fine, excellent. So, Professor Roy, I think
Yes,
you
sir.
can do the formal part of this thing. Yeah.
So thank you, Dr. Ghosh, for
Thank
your nice and presentation. It will be very beneficial to our participants. So if there is no question is there, so thank you very much. Thank you. So we can
you, sir.
end the session. Thank you.
Thank you, sir.
Okay, before ending the session, everyone, every participant must fill the feedback form that I have given in the chat box. Before leaving, everyone must fill up the feedback form that I have given in the chat box. Thank you very much. I think everyone have submitted the feedback response. Thank you very much. Please join in the next session.